Hello, thank you very much. So I'm going to be telling you about this project that I did with these three students. They worked on it for their thesis. They finished at Willamette University last spring, May 2023. And it combines a couple different ideas from folks who did these things before us. So here's the first idea. So we start with these rectangles. When I turn my head, the volume changes. That's weird. We start with these rectangles that have vertical and horizontal sides. They're looking in four directions, up, down, left, and right. And we have a graph, and we put a vertex in the graph when two rectangles see, for a vertex in the graph for a rectangle, and an edge in the graph when two rectangles see each other. So like A looks over to the right to see B, there's an edge. C looks down to see D, there's an edge. B and D see each other, even though they're right next to each other, that still counts. A can't see E because B is in the way. So you get this graph. So that's the first idea. Here's the second idea. So these things are called rectangle of influence graphs. So it's changed up a little bit. So now the vertices of the graph are points instead of rectangles. The edges are rectangles between the points. So you think of these 5 points as corners. So say A and B, for example, are opposite corners of a rectangle. You make a rectangle between them. That puts an edge in the graph. A and B have a rectangle between them, so there's an edge there. But like D and A, if you make that rectangle with A and D at the opposite corners, B is in the middle of that rectangle. That's no good. You want the rectangles to not contain another point. So you don't have an edge in the graph there. And the question one question you can ask is, how many rectangles can you get? How many edges can you get in this graph? Can you arrange the points to maximize the number of rectangles? And some folks worked on this, and they came up with this formula. So with n corners, you can get at most n squared over 4 rounded down minus n plus 2 rectangles, aka edges in the graph. So this is the stuff that we were working on. We called these things south corner rectangle visibility graphs. We're combining these two ideas. We have rectangles, which are vertices. We have the rectangles looking at other rectangles, but now they're looking diagonally instead of left, right, up, down. They're looking in this one direction, which we call south. If you turn your head, it's south. With a little bit of a weird looking. So they look in these quarter planes. So these quarter plane images here are supposed to be, so A looking, A can see B and C. But a weird thing happens when A sees B. This visibility gets cut off in this horizontal strip. So A can't see through to D because B blocks its sight. So there's not an edge between A and D in the graph. And again, we ask the same question that had been asked before. What's the maximum number of edges you can get? What's the maximum number of pairs of rectangles that can see each other, or this rectangle can see that one? And we came up with this answer, which was kind of surprising to us, which is the exact same number, n squared over 4 rounded down, minus n plus 2. And now you're thinking, well, there must be some sneaky reason why these two constructions, these two ways of envisioning rectangles seeing each other versus rectangles with corners, they must be the same things that you're getting from these two methods. But no, they're not, because, ta-da! Because here's examples where they're different. This graph you can get from these rectangles looking, but you can't get this graph from thinking of these things as corners. And the second one, you can get from corners, but you can't get from rectangles looking south. So they're the same maximum number of visibilities, the same so extreme examples, but not the same structures all the time. This is continuing on the next question. This is what we call just corner rectangle visibility graphs, where the rectangles are looking in 4 different diagonal directions, but each rectangle is only looking in one direction, and they get to pick. Each rectangle decides which of the 4 diagonals it's going to view. And again, we asked, what's the maximum number of views we can have? Here's what we think. It's 3n squared over 8 rounded down. The weird thing is this thing doesn't work for all numbers of rectangles up to 11. So we actually have examples of rectangles that have one more line of sight than this formula. The formula only starts working for n equals 12. Here are the examples. So for this construction of rectangles here, we get exactly 3n squared over 8. But for that construction of rectangles, we get 3n squared over 8 plus 1, but only up to n equals 11. And then it stops working, and then we think that 3n squared over 8 is the best. So this is the next question, that question mark there. With 13 rectangles, is it possible to arrange them to look in different directions to get 64 sites, or is 63 the most? As my contribution to the gift exchange this year, I have, there's puzzles that I developed based on this project and others that I've done with some other students. You can try some of these things yourself. Thank you.